Alright, here we are, last page of the first set of notes for our brief differential equations unit. So again, set of problems here where we will give you, or you will get, a differential. This is called the differential. It's giving us the pattern in the slopes, and in this case the pattern of the slopes is whatever the original function was. If you take the y-coordinate of the original function and subtract the x-coordinate, you'll get the slope of at that point. So down below, Mr. Friedland has used this URL to build two versions of the same slope field. The one on the left is a zoomed in version. The one on the right is zoomed out. So if we use these slope fields, and we'll do problem A here, we're going to sketch a solution through 0, 3. So if we do this over on the on the left hand side, we're going to start at 0, 3. We're going to follow the slope up if we're going off to the right, and as we come down to the left, the slope looks like this. And as we get down to this point in here, this series of slopes here, you notice that our function is asymptotic to this line that goes right through here. Now that line that goes right through there, these right here, each one of these slopes, all of these slopes are where the y value is 1 larger than the x value, which means the slope will always be 1. Tucked over here is the slopes where the y value is equal to the x value, and each one of these slopes is 0. So if we take and look at problem B here, I'll do problem B over on the right hand graph. We're going to start with the point 0, -3, which is right here. As we go to the right, you notice that the slopes end up being very steep and negative very quickly. So then our function is going to end up looking like this. Kind of it gets pushed, if you will, by the slope field down this way. And then when we're coming to the left, when we're looking at negative values of x, the slope is slowing down. It ends up being 0, and then it turns around and it's going to end up being, again, like the blue function, it's going to be asymptotic to this line of slopes right here, where the y value is 1 greater than the x value, or we get slopes of 1. Now, if we look at problem C, we've done this a couple times where we try to figure out what is the equation of the parent function. We're going to start with the differential and see if we can figure out what the equation for the parent function is by separating the variables. So we start with dy dx equals y minus x. We can multiply both sides by dx, which then is going to give us dy is equal to dx times y minus dx times x. And then you notice pretty quickly as we try to take and bring the y over to the left and leave the x over on the right, can't be done. This gets us kind of in trouble. And as it turns out, it's not an easy thing to do for us. We at this point give up, but if you continue with calculus, you will at some point figure out how you can solve this differential. And when you do solve this differential, you will end up with this equation right here. Now, though we can't solve the differential, we can show you that this here that I've highlighted in red is indeed the solution to the differential. It is the equation from which the differential came, if you will. So the way we're going to do this is, the way we're going to demonstrate that this is actually the solution to this differential, is we're going to compare both sides of the equation. By that, what I mean is we're going to start first with the solution. And again, the solution came by solving the differential. but somebody else had to do that for you. So if we start with the solution, and then we take the derivative of this, you would end up with dy over dx is going to be equal to, this would be unchanged, given that e is its own grandpa. So this would be 3e to the x plus 1 here. The other way we can do this, if we start with the solution, y is equal to 3e to the x plus 1. If we take at this point and we subtract from both sides x, then we would end up with y minus x, which is equal to 3e to the x plus 1. Now notice what this has just done for us. What we have is, when we took the solution we have been given and took the derivative of both sides, we ended up with that, 3e to the x plus 1. When we took the solution and we subtracted x from both sides, we ended up with that, which must mean that if the dy dx is equal to 3e to the x plus 1, and the y minus x is equal to 3e to the x plus 1, then these two must be equal to each other. Right? So we've taken the solution and showed that, yes, indeed, that solution works. Now, the final problem we're going to do here, problem E, we're going to take and use this form of the equation and show that we're going to solve for we're going to find the equation, we're going to find the equation that is going to go through this point on the graph, right? So that point on the graph would be up here, and you'd get a sense of what its rough shape would be up here. Right? It looked like roughly that. And if you were to do this, you simply take this point here and we'll plug it in for the y and for the x, and that's going to give us -2 is equal to c times e to the 0 plus 0 plus 1, which gives us -2 is equal to c plus 1, or c is equal to -3, which then gives us the parent equation that has the differential of y minus x that goes through the point 0, -2. That parent equation is minus 3e to the x plus 1. And then if you take this equation and you were to graph it on your calculator, you would find this little green function that I gave you up there. And we're done. Notes 1 finished. Thank you.